Hi guys. Okay, so we're moving on to last couple sections of chapter 2. We've got higher order derivatives. So far, just as a reminder, we've got the power rule. And the power rule says that the derivative with respect to x of some simple function raised to an exponent would be n times x to the n minus 1. Okay. We also have the product rule. And the product rule says that if y is equal to f times g, y prime is first times the derivative of the second plus the second times the derivative of the first. Okay. We've also got the quotient rule. Quotient rule is when you have functions like f over g, right? The derivative would be low d high minus high d low all over low squared. Okay, so we've got our three rules here: power rule, product rule, quotient rule. And this is not a new rule. Okay, so this is just telling you that you can take higher order just means more than one, right? So more than one. Okay, and we can take multiple derivatives of functions, especially polynomials, right? So if we wanted to take the first derivative, this is just term by term differentiation. This would be minus 5x to the fourth, right? And then bring down the 4 to get 20x cubed. So plus 20x cubed. And then plus 2 here. And that would be our first order derivative, right? Y prime. If we want to find the second derivative, so y double prime, we would take the derivative of the first derivative. So you just keep going. This would be negative 20x cubed plus 60x squared plus 0. And then triple prime, we could say, well, that's negative 60x squared plus 120x. Right? And the last one they wanted was the fourth derivative. And so we'll write Roman numerals there. We'll get negative 120x plus 120. And so higher order derivatives is simply taking derivatives of derivatives. Okay, and they introduced this topic because part of an AP exam, you're going to have to deal with what we call particle motion. Okay, this word rectilinear is talking about just right or left and a line. Okay, so particle motion, particles can go up, down, left, and right, and we know that in 3 dimensions. But AB calculus deals with simple particle motion where particles only move right to left. Okay, there's not going to be any up and down. It's just going to be considered in a line. And we learn these higher order derivatives so that we can come up with these definitions of the four main things that maybe you guys have seen in physics. But you have a position function. If you take the derivative of position, you get velocity. And if you take the derivative of velocity, you get acceleration. And then one you might not have heard before is if you take the derivative of acceleration, you get what's called jerk in physics. This is not on AP. This is just physics. It's just letting you know that that's true. Okay, and then we have definitions here, right? And definitions are big, right? I'm a definition-based teacher. We'll underline definitions, and that gives us a starting point. So whenever you're asked when a particle is at rest, the definition of rest is that the velocity is 0. If you're asked about movement, right, where is the particle moving, right or left? That depends on the definition. The definition of right is velocity positive. Left is velocity negative. Okay, acceleration, accelerating right is a positive and accelerating left is a negative. And speed, right? Speed, we don't care whether I'm going right or left. Okay, if I'm going 5 miles an hour left, my speed is 5. Okay, so all you have to do to get the speed is take the absolute value of the velocity. So we're going to definitely do this problem. It's a great problem. We're gonna do this after I give you another example that's a little bit easier. Easier because this function here is a little bit more complicated than, say, a polynomial. Okay, so let's do an example here. So these are not on the notes. If you guys want to grab a sheet of paper, you could copy down this example. Okay, you can always rewind it. So I'm gonna start by saying we've got a position function, and it's given to us. A lot of times in physics they use s of t or x of t, but either way it's the position. And I'm going to say that my position function is 1/3 t cubed minus 2t squared. And so I really want to take some time here to make sure you understand what's happening. So this is going to tell you the position of the particle at any time. Okay, and so for instance, if you plugged in, at time equals 0, right at the very beginning here, what is the position at time 0? It's 0 minus 0 or 0. And so what does that mean? That means that this particle, right, is only moving right to left, and it's at a position on your axis at 0. So your particle is right there. Okay? All right, and through calculus, we now can find simple velocity functions because our definition of velocity is s prime of t. The derivative of the position will give us the velocity at any time. And if I take the derivative, my power rule tells me 3 times a third, which is just 1, t squared minus 4t. Okay, and again, what does that tell me? That tells me the velocity of the particle at any time. Okay, so for instance, the velocity at time 0 would be 0 minus 0 or 0. And so when I start the clock here, this thing is at rest. Right? Nothing is happening at time 0. When I start the clock, this thing is not moving. Right? Now, we could find velocity at time 1, and that would be 1 squared minus 4 times 1, or negative 3. And so we know that after 1 second, this particle is moving left. Theoretically, we could go back and find the position, right? Where is it at time 1? And so all these functions are doing, or they're telling you specific things about where is the particle at particular times. Is it moving right or left or stopped? That's all you need to know about velocity. And then we can find the acceleration by doing the exact same thing. We could take the derivative of velocity, which gives us the acceleration function, which would be 2t minus 4. And again, what's the acceleration at time 0? At time 0, the acceleration is negative 4. So that's kind of weird, right? I'm starting in a position of 0. My velocity is 0, which means I'm at rest. But the acceleration at that exact moment is negative 4. And so even though it's at rest, it's about to start moving, right? Because the acceleration is going to pull that thing to the left. It's accelerating left, even though it's stopped. I know that's kind of weird, but we'll go through an example here. Okay, so what if they say find, right, left, right movement? Okay, so if they want to know about finding left and right movement, you better first find where this velocity is equal to 0. You need to know where is it at rest. And so if you start with your velocity function, which was t squared minus 4t, and you set equal to 0, you get t times t minus 4 equals 0. And so at time values of 0 and 4, the particle is at rest or stopped. Okay? And so if we do a simple velocity number line, obviously we're going to start this at time value of 0. 1, 2, 3, here's 4. Doesn't really matter. I just happen to have graph paper, so you just put 4 down. What we know, right, is that it stopped at these 2 times. Those are the only 2 times it stopped, right? Mathematics has told us that the time values of 0 and 4 plugged back in cause the velocity function to be 0, which is the definition of stopped. And so it's not randomly going to stop over here, you guys, at time 20, because mathematically we didn't get those zeros. So all we have to do is figure out, well, what's happening in between here? Well, what happens at time 2? We'll just go back up here at time 2. This would be 4, right? Minus 8, which would be negative, right? So your velocity is negative there. And what happens at time 5? Well, if I plug 5 in, 25 minus 20 is going to be positive, so my velocity is positive there. This is the definition of left. And this is the definition of right. And so analyzing particle motion becomes very repetitive. You find the velocity function, you set equal to 0. You solve and get those time values where the particle is stopped. You do test values to plug in and decide whether velocity is positive or negative. And then that tells you where it's left or right. And whenever you answer a question like this on an AP exam, you have to say, let's do left. We're going to use interval notation. This thing is moving left from time 0 to time 4. And you never tell me this without a definition. You always have to write since velocity is negative. That's the definition of left. Okay, then you would say, well, where is it moving right? It's moving right from 4 for forever. So we're going to use infinity in our interval notation. How come you know it's moving right? Since velocity is positive. That is the definition of right. Okay, so you have to make sure on an AP exam to give your interval and then tell me what happened or why. Okay, what about find acceleration? Acceleration right, left, right? Again, you need to first find where the acceleration is equal to 0. It's the same exact process, just one derivative below. And so you would take your acceleration function, which we said was up above 2t minus 4. And when we set that equal to 0 and we solve, we get 2t is 4, which happens when t is 2. So what happens when t is 2? Well, on your A line, not your velocity line now, starting at time 0, over here at time 2, we know acceleration is 0. This particle is not accelerating right or accelerating left. Okay, so what's happening at time 1? Well, at time 1, the acceleration will be negative. And at time 3, 6 minus 4 gives us a positive value. And so you would say accelerating left, again, interval notation from 0 to 2. How come? Since A is negative. And then you would say accelerate right when from 2 to infinity, since A is positive. Okay, so this is a very simple, I say simple, you guys, I know it's the first time, but this is a simple function that we started with, a polynomial. And polynomials give you nice and easy derivatives that you guys know how to take derivatives of. There's nothing complicated when you set equal to 0 because this is old knowledge of polynomials. And we have a lot of definitions here, right? Right, left, accelerate left, stopped, 0 acceleration. Okay, and all of this is just our intro to dealing with these particle motions, which are in AB calculus only moving right and left. Okay, so what changes? Well, what changes, you guys, is the function that you start with. Okay, and you can see here that this function is a little bit more complicated because it's got an exponential piece to it. Your derivatives will become more complicated, and then solving those things when you set equal to 0 will also be more complicated just because of the math that's involved. But the calculus definitions don't change. So we're given a position functions. You want to know where is it stopped, moving right, left, accelerate, decelerate, 0, all that stuff. Okay, so we're going to do the same process here. We have our position function as 2t e to the negative t, 2t e to the negative t. Okay, well, that is the same as 2t over e to the t. And so let's go through and find the velocity. All I did was bring that down, right? So quotient rule, we have low, d high, minus high, d low, the derivative of e to the t is e to the t, over low squared. Okay? All right? And the first thing we're going to do, since we want to know about moving right and left, is we better find where the velocity underlying definition is 0. Okay, so we're going to set this equal to 0, and now we're going to try to solve this. Okay? All right, so now that that's equal to 0, this gets more complicated because of the function. So again, I have this function 2e to the t minus 2t e to the t over e to the 2t. And where is that equal to 0? Well, when does a fraction equal 0, you guys? A fraction is going to be equal to 0 when the numerator is 0. So technically, you don't even care about this guy. We know that this is an exponential function, that it's never 0, right? So it's not an issue. We just need to know where is 2e to the t minus 2t e to the t equal to 0. Again, because 0 divided by some number is 0. So we're focusing on the numerator. We can take out our e to the t. And we have this, okay? And then what we're going to do here is try to solve this. Now, this takes some knowledge of this function e to the t. So this is a product of two terms. So this is going to equal 0 when e to the t equals 0, or when 2 minus 2t equals 0. This never happens. And again, remember we talked about this exponential function before. This exponential function is continuous. It's got a domain of all real numbers, and it's got the x-axis as a horizontal asymptote, so it's never going to cross the x-axis. So this is not going to produce any zeros for you. Here, this tells me that 2t is going to be equal to 2, or this will all be 0 if t is 1. And you could see that very easily. Plug in 1 right there, and 2e to the t minus 2e to the t is 0. Okay, so what the heck did we just do? We just found a time value of 1, which does what? It causes the velocity to be 0. So if you do a velocity line, and you put time 0 there, and time 1, we know right here the velocity is 0. And so we're going to check around it. Well, what happens at 0.5? Okay, so if you're at 0.5, okay, what would the velocity be? Well, let's just think about this right here. Half of 2, if we're plugging 0.5, half of 2 would be 1. And so I have 2e to the t minus 1e to the t. So this looks like it's going to be a positive value. And so here you would have velocity positive. If I plug in 10, this clearly is going to be 2e to the t, right? Come down here, 2e to the t minus 20e to the t. This is definitely going to be negative. And so you can now say this thing is moving right on the interval, right, from 0 to 1, open interval. How come? Since velocity is positive. Where is it moving left? It's moving left from 1 forever, since velocity is negative. Okay, so the clock starts, this thing moves to the right for 1 second, it then stops, and now it's moving left forever. Okay, so how do we get a of t? Well, a of t is the derivative of v of t. So we've got to come here and take the derivative of this velocity function. So this is low, d high. Okay, what's the derivative here? This is 2e to the t minus this guy here is going to be pretty complicated because this is the product rule, right? And so I think at this point, you guys, I'm not going to keep going here. I was a little bit hesitant. That's why I did that other example. I'd like to stop there, okay? And then what I'll do is I'm going to post probably another example of a simpler function where this acceleration doesn't get as ugly, okay, as this. Now, to be honest, after we learn a different derivative rule, this gets a lot easier. But I do want to stop there for now, and then we'll do another one in a different video. Okay? All right, guys, take care.